glad to have Henry Richman from NCTS, and he will talk about the Ricci flow on graph.
Thanks everyone for coming to listen, and thank you to Professor Liao for this invitation. Right, so today I want to talk about a project I have with several co-authors. I guess I didn't want to put them all on the first screen, so the names will come up later on a later slide. But the idea I want to talk about today is a definition of Ricci flow for graphs and how it has satisfied some analogs to Ricci flow for manifolds. Okay, right. So to start out as motivation, though, I want to say a bit of why we might want to understand the geometry of a graph. So by graph here, in the applied world, these are often referred to as networks, but this consists of some collection of nodes, usually a finite set of nodes or vertices, and then a set of edges that connect. So each edge connects a pair of nodes. Sometimes in applications, these might be directed. So I think in this figure that I took, these show directed edges. But for most of this talk, I will only consider undirected graphs. And networks often appear in real-world applications. So this example is taken from a paper that studies trade relations in international trade. So each node here corresponds to a country, and arrows correspond to trades between countries. And given some representation of this as a network, we might want to study the network and answer some questions that are useful to economics. So for example, we might want to know, like for a given country, are they vulnerable to having their trade cut off if their relation with certain countries is bad? So we might look at like edge cuts on the graph and things like that, or right, maybe we could study centrality on a graph to have a way of describing a country's importance within a trade network. So right, and when we're talking about economics, there's probably a lot of other things that are important that are relevant here, other than just the graph theory. But graph theory could play one input to understanding this kind of economic problem. So right, so given some real-world network, we often want to solve problems like max flow min cut, or solve community detection problems, and this will be useful somehow to the real world. And there have been many proposals for algorithms to do this efficiently for large networks. And right, so we'll discuss one tool we can use, one additional tool, where the math background we're going to use is some ideas coming from differential geometry, and then some ideas coming from combinatorics and electrical methods. Right. So for the differential geometry background, we're going to define an analog of Ricci flow. So what is Ricci flow to begin with? So maybe just to get a sense of the audience, who here has seen a definition of Ricci flow before, by a show of hands? Okay, I assume I heard there's like some differential geometers in the department. So I guess if you study differential geometry, this will be a very like simplified explanation. But right, so motivation. One big reason that Ricci flow became a popular topic is it was used to solve the Poincare conjecture, and the Poincare conjecture was some conjecture on what conditions on a given manifold of a given dimension which suffice to show that that manifold has to be homomorphic to a sphere. And the idea of Ricci flow is starting from arbitrary manifold, if it satisfies certain initial conditions, we can apply this Ricci flow to the manifold to deform it over some process and get it closer and closer to the sphere. And if we run Ricci flow for long enough, we'll end up with a sphere if it satisfies the right conditions at the start. And the way Ricci flow works roughly is for areas on the manifold with positive curvature, we shrink the metric. And then vice versa, for negative curvature, we expand the metric. So here in this cartoon of some surface, we have areas on these two sides. The curvature is positive, so we would shrink that under Ricci flow, and then in this neck in the middle, we have negative curvature. And we would expand this area under Ricci flow. So if we expand this neck part and shrink the sides, we could sort of visualize that we are going to turn this closer to a standard sphere in the standard embedding. Okay, sorry, and yeah, I wanted to add, one thing I wanted to add to this though is, so we have this definition of Ricci flow, and then we said our goal is to take some manifold and either get it closer to a sphere, or maybe get it to some other standard manifold if it's not homeomorphic to a sphere. But one property that is useful to have for Ricci flow, in order to do this successfully, to make an arbitrary manifold get closer to the sphere, we would at least want the flow to not have periodic orbits. So one, I guess I'll. So at least there's no non-trivial orbits under Ricci flow. Right. So if we start some manifold and we get a periodic orbit, then it might never reach some standard manifold like the sphere. And I'll come back to this property sometime later. Okay. So then the other. Right. So that's kind of the ideas from differential geometry we're going to be using, and then from more on the combinatorial side, we're going to use this concept of effective resistance. So this is an idea that was actually sort of first studied in an applied sense as well. So when scientists start studying electricity in the 1800s, they discovered you can combine resistors in various circuits, and you'd want to so if you have a bunch of resistors like this and you combine them in this way, you'd want to know what's the resulting overall resistance between these two terminals I and J. Right, so it turns out there is some number here, and there's a way to compute this number. And so these ideas on the rules on how to compute effective resistance are all fairly old, but they have showed up in recent work as well. So this isn't so close to what I'll be talking about today, but effective resistance was used in some recent results in the 2000s for efficient ways to solve the traveling salesman problem and other kinds of applied results. And right, it turns out studying effective resistance is also related to probability theory, because the formulas for there's theorems that relate effective resistance to things like simple random walks on your graph and to sampling random spanning trees on your graph as well. So these are things that probabilists would care about. Right. So to now say a bit more about how you actually compute effective resistance. So the first cases are these simple ways to combine two resistors at once. So we can combine them in series like this, and in this first figure. And if we combine two resistors in series, their overall resistance will just be the sum of the individual resistances. And there's also a way a second way we can combine them is in parallel, like shown in this figure. And in this figure, there's also a straightforward formula for the overall resistance, which looks slightly stranger, but another way to express this is you take the reciprocals of A and B and you add them together, and then you take the reciprocal of that stuff. Okay, so we have simple rules for series combinations and parallel combinations. So what about the general case? So if we say, go back to this example on the previous slide, so is it possible to use just a series in parallel rules to compute the effective resistance on this circuit at the bottom? So maybe by show of hands, does it seem like this should be doable using these two rules? Okay. Are there any questions so far about these definitions?
Yeah, there might be consensus that the two rules are not sufficient.
That's right. Yeah, exactly. So here in this example, it is possible to calculate the overall effective resistance using just these two rules. And if you find the rest of my talk boring, you could just try to compute this, I guess, as an exercise. But there are in fact examples where the series rule and parallel rules are not sufficient. So in this example, in this circuit known as a Wheatstone bridge, we have 5 resistors combined in this way, and it's not possible to reduce this into a bunch of series rules and parallel rules to get the overall effective resistance. And this is the minimal example where that goes beyond the series and parallel rules. So it turns out in this particular circuit, if we have the resistors just represented by variables A, B, C, D, and E, we can write down this algebraic expression for the overall effective resistance, but it has a lot of terms showing up. So it's much more complicated than the first two rules. And it turns out there's, we can write down a formula for the general case as well. That goes beyond just the series and parallel rules. So this general formula for computing effective resistances, it involves looking at spanning trees on the graph. So what we're saying in the denominator is we take some sum over all the spanning trees of our underlying graph, and then in the numerator we take not just the original graph, but we take some quotient of the original graph. So we take the two terminals I and j and we glue them together like this, and then we take spanning trees on that quotient graph. And then within each of these, we take a sum of spanning trees, and each spanning tree corresponds to a single monomial in the expression. So we see that combinatorics are coming up through this looking at the set of spanning trees, and this was already known in the 1800s through the work of Kirchhoff. So as one example, to say one example of the effective resistance, if we take, say, so one possible spanning tree is taking these 3 edges, and these 2 edges are deleted. So if we delete edge B and D, what's left over, this is a spanning tree. All right, I guess I didn't give a definition, but a spanning tree means the subgraph is connected and there's no cycle. So removing B and D gives us a spanning tree. So we see that there's a BD term that shows up here in the denominator. And it turns out every term in the denominator corresponds to exactly one spanning tree in this way. And then doing this for the quotient graph, spanning trees here will correspond to the monomial in the numerator.
What is the notation TTG?
Oh, here. Yeah. The curly T is the set of spanning trees.
The set of spanning trees. So you mean a graph has many spanning trees?
Right. So in this case, for our example graph, this is one spanning tree. Another spanning tree would be, say, if we take these 3 edges and we delete edge A and edge C. So we also get a spanning tree here. And so we'll also see there's an AD term that appears.
Would you say again the definition of a spanning tree?
All right, a spanning tree has, it's connected and it has no cycles. So it's so we need to remove enough edges to remove all the cycles, but not too many edges where it makes the graph disconnected.
So I guess in the formula, the straight T is a spanning tree.
That's right. Yeah. So here the straight T is a spanning tree inside the side of E.
E is the vertex or edge.
And then E is an edge.
And what is this number L?
Oh, right. LE, I guess I forgot to mention. LE is just the resistance on that edge. So we're studying, yeah, we have graphs, and on each edge of the graph, we have a resistor within that edge. And that resistor comes with some positive real resistance.
Thank you.
And yeah, so perhaps in a simple case, we could first think about all resistances all resistors being unit resistant. And in that case, these products are just one. So when we have unit resistances, this formula just has the number of spanning trees on the bottom and the number of spanning trees of the quotient graph on the top. I think that, yeah, any other questions about this example? So for the Wheatstone bridge graph, we have this expression for the effective resistance, and we can't get this from just the series and parallel rules. Okay, so one fact that's very important for effective resistances is this property known as Riley's law. So Riley's law says if you take some circuit with some terminals I and j, where you're measuring the effective resistance from I to j, if you take any edge in your network and you increase the resistance of the resistor on that edge, so we're taking this partial derivative, then the overall effective resistance has to also increase. So it's not possible that I take a single resistor, increase its resistance, and somehow the overall resistance decreases as a result. Okay, so this is a property that it should be fairly physically obvious. Like if we had the opposite behavior, that would be very counterintuitive. But it turns out, it turns out this like obvious expectation is in fact true. But it's not so obvious mathematically. So what we just saw on the previous slide is for the Wheatstone bridge, this is our expression for effective resistance. And let's say we wanted to, this middle edge had resistance C. If we increase the resistance on C, our claim is that this overall expression should be non-negative. And I think, I'm sure all of you have learned calculus where you know how to take this derivative, but it's not something you can just write down very easily and observe that it's positive, right? So if we apply the quotient rule here, we have positive terms and we have negative terms. It's not so obvious where every single term is just positive after taking the derivative. Okay, so it is. Right, so maybe just to check, has anyone been able to, like, can anyone tell me what the expression here is if I take the partial with respect to C in this derivative? And justify justify the sign on this expression. Yeah, so maybe this is, if you want to know the exercise, you can close your eyes for the next slide. I'll show the answer. So it turns out this is the resistance. This is the partial derivative. So it actually simplifies as a perfect square, and the fact it's a perfect square means that it has to be non-negative. So we see that here the denominator, inside the square, the denominator is the same as before, but then in the numerator we have some different expression coming out. Right, and so it turns out this is always the case. If we take a partial derivative, it's actually a perfect square.
How do you describe the numerator?
So you can describe it by saying, So if we take, so we have this BD term. So what we're doing is, let's say we remove B and we remove D, and then in this expression we're taking the derivative with respect to C. So then we're looking at what happens along C. So if I I don't know if I'll be able to give a full explanation, but roughly it comes down to if I delete edge B and C, and then I send current from I to J, it's going to pass through the edge C, so I'll get a plus or minus sign in front of the B. If I delete A and D, and then I send current through this way, the current does not go through edge C, so that means I don't have a AD appearing in this formula. So yeah, it is possible to explain like what each of the terms stands for in the summary. But I think won't be able to have time to like give the full corrective solution. But yeah, there is interesting combinatorics behind formulas.
The minus sign is because of the direction of the current on the speed.
That's right. Yeah, yeah. If we go to AE instead, the direction is reversed. Other questions on this derivative? Okay, yeah. So another special case of Raleigh's law is that we can use this to say what happens for deleting edges and contracting edges. So deleting an edge, yeah, I guess deleting edge. So if we look at edge C, and this is our original network, when we delete the edge, it's like just taking out that resistor from the network. So we get this network as a result. But you can think of this as taking a limit where you have that resistance go to infinity. So increasing the resistance to infinity is the same as cutting the wire completely. So that way no electricity can flow through the edge. So we can think of this as one extreme case of Raleigh's law. The effective resistance has to increase when we delete any edge. And then the other extreme case is when we contract an edge. So in our example here, if we take edge C and contract it, it means we take it to endpoints and we glue them together. So in this case, we can think of this as taking the resistance and sending it to 0. When the resistance goes to 0, that means like the two sides of the endpoint have to have exactly the same voltage. So it's like we just glued them together within the network. So this is also we can think of this as one case of Raleigh's law where contracting an edge has to decrease the effective resistance between any two terminals. Right, so now we finally have gotten to the main definition for this talk. So here, this is a proposed formula for an analog of Ricci curvature on a graph. So typically this will be for a finite graph. Our expression, it involves, so on a given edge, say the edges between vertices vi and vj, we have two terms that correspond to the degree of the two endpoints of E. And then we have a term that uses this effective resistance, omega. So the effective resistance across the edge. And then we also divide by the resistance on that edge, individual edge itself. Okay, so I'm not going to really say much about why we use this definition at this point, but I'll come back to that later, where the intuition for, I guess, the motivation for using this edge curvature formula.
So you what is omega E?
Omega E is the effective resistance across the edge E. So yeah, I'll
including A, E, or not including E?
Including E. Yeah. So yeah, maybe I'll. So in this case, so yeah, using this formula, the notation I'm saying edge E goes between vertices I and J. Here in this case, on one side, this vertex has degree 3. There's 3 edges connecting here. On this edge, in this example, the degree is 4. And then so the curvature. Right, so here I'm dividing by the resistance that's on this edge. Here, the notation I was using earlier was omega ij. So this omega E means the effective resistance from one endpoint of the edge to the other point of the edge.
But that doesn't include E. You said it includes E.
It does, but it does. So I, right. So when I measure this effective resistance, I can still include E on this edge.
So
and
E, the line E is still there when you define omega E.
For this, right. Yeah. So it's Yeah, often in many cases, you care about the effective resistance when you delete the edge, but here I want the effective resistance when I keep the edge. So, like further out in the graph, I might have, in general, I'd expect there's like other paths that go from this endpoint all the way to the other endpoint that can avoid the edge. If there's no other edges, if there's no other paths to get from this side to the side that don't go through the edge, this formula will simplify. Right, so the main interesting part in this formula is this effective resistance term. And yeah, so we'll look at some more examples in a little bit, but yeah, before going on to that, I want to mention that there are some to say a bit to give some justification for why this is a nicely behaved definition of curvature. We can look at examples where we can look at example graphs where the edge curvature is constant. So in this first case, if we take a complete graph, it turns out every edge. So by symmetry, every edge has the same curvature, and it turns out this will be some positive amount. And we can think of this complete graph as being analogous to a sphere. Now, a sphere has positive Ricci curvature. So in the middle, if we take some grid graph, so we can think of this as some infinite graph in a 2D plane, like where the lattice point is connected to its nearest neighbors. It turns out in this case, according to this formula, every edge has zero curvature, and that kind of matches with how in the flat plane or flat Euclidean space, the Ricci curvature is zero. And then finally, if we take, in this last example, if we take an infinite trivalent tree, so again, this extends to infinity, then applying this formula, we have negative edge curvature on every edge.
So your examples, the edges are equally weighted?
Yes, yeah, here I'm assuming all equal edge weights. Yeah, changing the edge weights will change the curvature, except in the SAS case. In the SAS case, if you're a tree, it turns out the edge weights don't end up mattering. Right, and so in one way to justify this, or yeah, maybe at least one nice property of this choice of edge curvature is that we have a nice global relation on the total edge curvature for any finite graph. So it turns out if we sum over this curvature over all edges, we have one term for the degree terms, and we have another term for this effective resistance term. And so for this first term with the degrees, it's a straightforward graph theory to see this comes out to the number of vertices. So here this is the number of vertices. And then for the second term, it's this result of Foster from the 1950s, that this comes out to the number of vertices minus 1. So if we combine these two things, we see that the total edge curvature in this formula is always equal to 1 for a finite graph. So in particular, that says, like in this first case where we have a finite graph and we have it's symmetric, so all edge curvatures have to be equal, then the edge curvature just has to be 1 over n in this case. And then for this infinite graph, we can't apply this formula. So this formula doesn't hold on this, I guess, for either of these infinite graphs. Right, and then so I should say here that this is not the first definition of curvature for graphs that has been suggested. There has been many. There has been a lot of work trying to define analogs of Ricci curvature for graphs, and some of these assign a curvature to edges, and some of these assign curvature to nodes. And so here I just want to mention that when you only assign edge curvatures to nodes, you get slightly less information than when you assign a curvature to all of the edges. So in this case, all the nodes are symmetric in this graph, but they're not, like looking at all edges, they're not symmetric for automorphisms of this graph. Yeah, so it's, I guess in a way, it's nicer to define, to be able to define edge curvatures to understand graphs. Right, so okay, so now that we have a definition of a curvature on the edge, we can use this to define Ricci flow. So Ricci flow says we want to change our metric according to the negative of the curvature. Right, so our metric for a graph, the metric will just be these resistances, the individual resistances on each edge. And we have this curvature formula, so and we have the minus sign. So when the curvature is positive, the length decreases. When the curvature is negative, the metric should expand. Right, so now we can ask, with this, under this definition of Ricci flow, what should happen to maybe some example graphs. So we'll be able to look at two examples. One, a regular, like a finite grid, and then another network will be this Crotty plus graph that comes from like sociology. And I can show a demonstration. Okay, so I use Python to implement this Ricci flow under some choice of like finite step size. Okay, sorry. This is a Crotty plus graph. Right. So I mentioned earlier. I mentioned earlier that for a infinite grid, all the curvatures are zero. So if we apply Ricci flow, nothing happens to the graph. But if we take a finite grid, we do get some non-trivial behavior. So what happens here is that along the boundary of this grid, we have positive curvature, and Ricci flow will shrink the edges on the boundaries. And then in the interior of this grid, the edges have negative curvature, slightly negative curvature. And under Ricci flow, they will expand initially. Okay, so that's the initial behavior. It's different for the boundary and for the interior. But then after we run this, after a certain number of steps, we see a change in behavior, and now all of the edge curvatures become positive. So I guess it's pretty hard to see here, but it's colored light blue for being slightly positive curvature. But you can also see these numbers show the resistance on each edge as we apply Ricci flow. So now, at this point, everything is decreasing. And at some point, for some of these edges on the outside, if the edge approaches zero, then we would need to contract the edge, since we don't want the edge to become negative. Okay, and yeah, so running this past a certain point, you end up seeing this strange behavior because things are going past zero, so then the computations don't really make sense the way it's implemented. Okay, so that was one example with a fairly simple graph. And then in this other case, this Crotty club graph comes from a study where each node here represents a person in a club, and then the edges represent friendships inside the graph. And then this is a standard graph that's used to study community detection. So given this network of people and their relationships, community detection is a question of whether you can split up the people into natural communities, where within each community you could have lots of connections, but you want few communities in between different connections. And I guess, so in this case, running Ricci flow, you see it's a bit harder to summarize what's happening, but you do see, at least you see more extremes on like very positive edges, very positive curvature edges, and very negative curvature edges. But in this case, if we run this for enough time, though, eventually all of the edges will be contracted, and we'll end up with just a single vertex.
So what is the meaning of Ricci curvature in this case?
Like
communication?
You mean like mathematically, or as
in this what is the concrete meaning?
Well, I guess what I would explain to someone, like just on the applied side, is that it's some technical tool, and if you it's some tool where on some arbitrary network, when you run Ricci flow, the edges that are close together will tend to the edge between them, if they're close together, will tend to shrink and bring them even closer together. If they're far apart, Ricci flow will tend to increase the distance between them. So I think I didn't manage to prepare an animation for this, but there's some standard graphs that would show this behavior. So if we have an example graph where, let's say there's like two sides of nodes that are very well connected, then there's only a few connections in between them. In this sort of graph, if we start out with this and run Ricci flow, we'll see that on each side, these edges will get smaller, and then for these edges connecting different groups, these edges will increase. So it should, at least in these extreme cases, Ricci flow is going to, the Ricci curvature is matching the kind of expectation from just a heuristic sense.
So what is the Ricci curvature in the language of actual time? That example is about people communicating with each other.
Right. I suppose if you wanted to give it some meaning, you could interpret it where effective resistance can be connected precisely to random walks on graphs. So if you look at, say, random walks in this network, that might match up with like how communication can spread within the network. But I think I'm not sure how useful like trying to do this kind of translation is. I think to an applied person, what actually matters is if it performs well on benchmarks, rather than being able to give some explanation in terms of the theory. So and if you're so I think for someone who does just this applied math, I don't have some detailed explanation for the reasoning for this formula, but from a math perspective, there's some more substantial things to say about where this expression for Ricci curvature comes from for a graph. Okay, any other questions?
So LE becomes 0 or infinity within finite time?
So LE cannot become infinity in finite time, but it can become 0. It generally will. Some edges will go to length 0 in finite time. But yeah, that's a good point. So just like with Ricci flow on manifolds, you often develop these singularities, and you need to do something more clever to go past singularities. So now, so we looked at what this graph Ricci flow looks like on some examples, and we can also try to ask if it satisfies some nice properties from Ricci flow for manifolds. So I mentioned this thing at the start. For Ricci flow on manifolds, there's no periodic orbits that are non-trivial, at least. But it's also, it's invariant under scaling, so the Ricci curvature doesn't change if we scale the whole manifold globally. It also, if we run Ricci flow on a manifold, if we start with a manifold with non-negative curvature and then run Ricci flow, that will decrease the volume of our manifold. And then also, if we start with some initial manifold that has non-negative curvature and run Ricci flow, all of the manifolds we get in the future under this flow will still have non-negative curvature. So if they're roughly sphere-like, since spheres have positive curvature, we can think of this property as saying like this close enough to a sphere, then, and we run Ricci flow, it's not going to get any further from being a sphere in the sense of developing negative curvature. So these properties are all true for manifolds, and then we can ask if the analogs are true for graphs in this definition. So the first thing, invariant under scaling, is fairly straightforward to check that this is true for our formula. For graphs, it's also true that we have this volume decreasing property, where by volume for a network, I mean taking the sum of the resistances over all edges. And that's because I can think of the resistance as kind of the length of the edge, because like physically the length of a wire is actually proportional to its resistance. So the length will be the one-dimensional volume. But we have a slightly stronger property for graphs because it's not just true under some assumption, but it's true for an arbitrary graph, an arbitrary finite graph, because of this property from Foster's theorem. So so maybe as a reminder, for any finite graph, if we sum over the edge curvatures, that always sums up to 1. So we always have like positive overall curvature on a finite graph. Okay, and the third property, that starting out with a graph with non-negative curvatures, it turns out if we run Ricci flow on that graph, the resulting graphs will also all have non-negative curvature. So this is, I guess, the main result in this paper with co-authors. And then this last property of periodic orbits is still open. We haven't been able to make progress on this. So this is something I'd be interested in trying to make further progress on if anyone has ideas on how to do this. Okay, so this theorem from the third property mentioned before, if I take a positively curved graph, then Ricci flow preserves this property. So this was a project at a workshop organized by the AMC where Mark Kempton was the faculty mentor for this project, and the rest of us, we were postdoctoral graduate students in this group. So I want to say a little bit about some main ideas behind this proof. So what do we need to do here? So what we want to say is if we have, if we run Ricci flow on our graph, so if we have some graph and we run Ricci flow on it, we want to ask how does this curvature change over time as we're applying Ricci flow. And so the first thing we can do is we can apply the chain rule where we separate it over influence of all the individual edges. And then we see that for this first term, the change in the curvature, so after just applying the chain rule, we see that we need to just understand how the curvature changes as we change a single edge, or a single resistance within the graph. And it turns out these can be, we can prove some lemma by applying Raleigh's law. So Raleigh's law was saying how does this effective resistance omega change when you change a single length? And so it's just slightly more, a slightly longer computation to do this for the expression of the curvature. So it turns out what happens is if we take an edge E, if you look at the curvature on some edge and we increase the resistance of that same edge, that will always increase, weakly increase that curvature. But if we take the curvature on some edge and then increase the length of some different edge, it will decrease the curvature on that edge. So this lemma shows that the two cases split up sort of nicely into two contrasting cases. And then so I think that's all I wanted to give from the pieces coming from this proof. And then there's a bit more involved in combining these properties together, looking at the overall change in the curvature. But maybe one thing I want to mention is what this proof shows is actually that for an arbitrary graph, if we look at the minimum edge curvature, that always has to increase under Ricci flow. So even if we don't have this assumption, even if we start with a negatively curved graph, the most negative curvature is going to increase under Ricci flow. I don't know if there's some analog of this for manifolds. I guess yeah, didn't study that much in differential geometry, so I would be curious if this is analogous to some property of Ricci flow on manifolds. Okay, so any questions? I think after this I'm going to move on to describing some of the motivation behind this edge curvature formula, where this, like the math behind justifying this formula. But any questions so far about these results, properties of Ricci flow on graphs?
What happens if the time derivative of k is 0?
Where
rigidity.
Sorry?
If you have constant k curvature, what happens in that case? You're constant in time. I mean, capital K is constant in time, constant in E. Then what can we conclude about the graph?
Oh, I'm not. I don't know if a complete classification, but I do know that I guess one case where this holds is for trees. So on a tree, the curvatures don't change under Ricci flow. So if G is a tree, so if there are no cycles in G, then okay, so the degrees, these degrees don't change because they don't depend on the resistances. But in particular, right, so the special thing that happens on a tree is that this effective resistance between the endpoints of the edge is just equal to the resistance on that edge itself. So if we have some tree, this effective resistance from I to j is just equal to the resistance of the individual edge itself, because there's no other ways to get from one endpoint to the other. So because of this property on a tree, this last term simplifies to just 1, and then this expression doesn't depend on the length at all. Okay, so yeah, so trees all have this property that the derivative of the curvature is 0. But it's not all of them. So another example is for cycles. So if G is the cycle, and even if the lengths are different, it's also true that the curvatures will not change over time, like not change under Ricci flow as well. So yeah, if we run Ricci flow on the cycle, all of these edges will have positive curvature, and so under Ricci flow it will shrink, but it will shrink just under some global scaling factor, and the curvature will change. Yeah, so yeah, maybe I could have mentioned. But yeah, so trees and cycles all satisfy this property. I don't know if any other examples, but I'm guessing there could be other examples.
They say you have an inequality of omega ij when the graph when E is deleted or contracted. Is that inequality coming from equality, second equality?
Yes, right.
What is that equality?
I don't know it off the top of my head, but I know some reference I can share, but that says exactly like when you compare the effective resistance to the edge deletion, you can write down the difference as some perfect square. And yeah. So it's I think there might be some textbooks that I know of that I can send links to.
So is omega ij the Euler characteristic of some chain complex in homology theory?
I think it would be really interesting to show that. I don't know of any construction like that. Yeah, so saying, yeah, I think giving other interesting interpretations like that would be something to look into. Any other questions about these questions? Right. So I guess it might have been clear already that I haven't really studied. I'm not really a differential geometer, and I'm not. Right. So these ideas from Ricci flow are things I've only read about kind of recently. But what I did study as a graduate student was tropical geometry. So tropical geometry is a way of looking at graphs as analogs to one-dimensional, as analogs to algebraic curves, and in particular looking at algebraic curves over non-Archimedean fields. So things like the p-adic numbers. When looking at the p-adic geometry of an algebraic curve, it turns out there's a natural underlying graph that shows up, and tropical geometry studies analogs of things like divisor theory on algebraic curves, the divisor theory on graphs. So in particular, I guess a lot of motivation for tropical geometry came from arithmetic geometry first, where we want to do things like bound the number of rational points on a curve. And so again, as a very high-level overview, if we have some curves and we want to bound the number of rational points, we often want to, so instead of only looking at the curve over the rational numbers, we want to look over completions of the rational numbers. So for all the different prime numbers, we would, the integers could be completed to the p-adic integers, and you can also do this for rational numbers. And so you can try to understand all of the p-adic points on the curve for all primes t, and also look at the real value points or complex value points on the curve, and combine all this local information to get a bound at least on the number of rational points. So, one tool is using p-adic completion. The other tool is putting the curve inside of its Jacobian. So a curve, typically when we think about a curve, we would look at some affine equation, so equation in affine space or perhaps in projective space. But it turns out every curve also naturally embeds into its Jacobian, which is an abelian variety. So the geometry of its Jacobian, along with its embedding, can induce some sort of geometry on the curve as well. So using this tool, by looking at the curve inside its Jacobian, there's a natural flat metric on the Jacobian because it's a because it's a group. A group has this harm measure, and then that comes with some geometry, and we can use that to induce a geometry on the curve, and then also, the global information over the p-adic completions can often give us information about rational points as well. So it turns out that so this is one way of explaining where this formula for the edge curvature comes from. So when we take, so there are two analogous cases here. One is for algebraic curves, and one is for tropical curves or metric graphs. So in the case for algebraic curves, when we embed a curve into its Jacobian, we pull back the flat metric on the Jacobian to that curve x, we end up with what's known as the Bergman measure. And this, I guess, this shows up in various places when studying, the classical study of Riemann surfaces and things like, studying Riemann surfaces. But then, if we change from looking at the complex numbers completion, if we look at a p-adic completion instead, the relevant analogous measure is known as the Young's canonical measure. So here, again, we can embed the curve in its Jacobian, which has non-Archimedean geometry, and the analog for this Bergman measure can be expressed as two pieces. There's a discrete piece that can be written as a sum over vertices, and there's a continuous piece where we have a sum over edges. And then coming from this formula, we can sort of simplify things down a bit and kind of average. So this formula, this is a measure over all of the points in the graph, and then by sort of averaging out this formula over the edges, we end up with this expression. Okay, so yeah, so the sort of the hidden mathematical meaning behind this formula for edge curvature is it's expressing the geometry of the non-Archimedean Jacobian attached to this graph.
So how do you get a graph from a curve?
Right. So maybe okay. So I mentioned this I guess in this one bullet point. So when we start with a curve, we typically want to start with a smooth curve, and so it's smooth over, say, the p-adic integers. But when we have a smooth curve over the p-adic integers, we can reduce mod p, and so that's a map. Sending p to 0, we go from p-adic integers to just a finite field of p elements. And then if we start with a smooth curve over zp, and then reduce mod p, we can sometimes end up with a singular curve. So with a singular curve over fp, we can take the dual graph of that singular curve. We have we put a node for every component on that singular curve, and we put edges corresponding to nodes, like singular nodes that appear. And so that's a way to get, or that's one way to describe like the relevant graph. How we go from, we can start with some curve over rational numbers, we pick some prime p, and we end up with a graph that sort of encodes the p-adic structure of the curve. But another answer to this question is, like a more modern description of where the graph comes from is we're taking the Berkovich analytification. So this is some process for over any non-Archimedean field, and there's also some graph that lies inside that as well. But yeah, I guess these terms are kind of technical. I wasn't planning to describe all of these.
So the graph depends on p.
That's right. Yeah. If we fix a graph over rational numbers and we pick different p's, we will get different graphs corresponding to different p's.
But the real is another completion.
Right. Right. So I think what you get over the reals is sort of the classical case, and where you don't get any graph attached to that, as far as I understand. But you get a graph only when you look at the like prime these like non-infinite spaces. Yeah, and I guess I wanted to mention briefly. Yeah, so I guess this is the like the take-home point about where this formula comes from. But so I made this claim that the Bergman measure is analogous to the John canonical measure, and one way in which we see this analog is when studying Weierstrass points. So when studying like higher degree Weierstrass points on a Riemann surface in the classical case, it turns out when you take a divisor of high degree, the Weierstrass points will distribute according to this Bergman measure. And then, I guess I'm not, due to lack of time, I'm not going to say anything about what Weierstrass points are, but it's some classical construction for Riemann surfaces. But then you can do the same process on say a curve over a p-adic field, the non-Archimedean field, and then it turns out we also get some limiting distribution at the Weierstrass points where the limiting distribution is this John canonical measure. So yeah, this is one way in which we can say precisely that they serve analogous positions. And yes, and I think here too, I guess I'm running out of time, but these sorts of ideas to apply like study properties of effective resistance is not only useful in applied math, but it's also has been used in certain results within arithmetic geometry as well. So there's this like a famous conjecture within arithmetic geometry, the Bogomolov conjecture. It's some statement about kind of like it's sort of like bounding rational points on abelian varieties, but looking at a generalization of this, which is bounding points of small height on abelian varieties, and there was a certain special case of this conjecture, which was solved by studying properties of this effective resistance function on a graph. And one slight detail, though, is effective resistance function. In this case, we're not only thinking about it as like between vertices on the graph, we can sort of generalize it to a continuous function where we take points in the interior of edges as well and still measure effective resistance. Right. So this has been used to prove some important results, but there's also still like some open questions involved about the structures that I'm hoping to work on more in the future. Right, and then maybe to go back to some questions about just Ricci flow from graphs, some open questions that I would hope to work on more are this question of can we prove the non-existence of periodic orbits for finite graphs? Can we talk about Einstein graphs? So these are graphs where if we run Ricci flow, we get the same graph up to scaling, or this is how they're defined for manifolds. And there's also certain properties about if you take, for manifolds, if you take a product of two manifolds where one of them has negative curvature, I think there's results saying like, in some sense, this product will also have negative, maybe either positive curvature or negative curvature. So I think that it would be interesting to be able to answer this for graphs as well. Okay, so that covers what I want to talk about.
You mentioned these well-shot points. So you have these well-shot points on graph. Would you show us some examples and why they are special?
Sure. Right. So, I guess for Weierstrass points on graphs, so at least for algebraic curves, I guess if some people in the audience have seen some theory of algebraic curves, if x is a hyperelliptic curve, then these Weierstrass points are they're fixed points of the hyperelliptic involution. So, I guess often hyperelliptic curves are some specific type of higher-genus curve that's a bit simpler to study in general, and they come with an involution, and the Weierstrass points give us a fixed point of this involution. But one way to see this on a graph is if you have this simple sort of graph with two nodes and then a bunch of parallel edges between the nodes, the Weierstrass points will just be the midpoint. So at least in this case, we have the analogous property, like there's an involution here that interchanges the two edges, and it turns out Weierstrass points will be the
Weierstrass points are not necessarily vertex.
That's right, yeah. When you add more parallel edges, the behavior is a bit worse. It's a bit less well behaved, so you don't only get points in the tropic case, you can get positive length intervals as well. I guess other simple examples is if you take a complete graph on four vertices with equal edge lengths, the Weierstrass points will just be the vertices. And the result that I mentioned, I guess here what I'm drawing is specifically Weierstrass points for the canonical divisors. And the result I mentioned on my slides looks at this generalization where you take some higher degree divisor, not just the canonical divisor. But I think for this definition, it started out by looking at this case for starting with the canonical divisor. I think one reason they were important to algebraic geometers is it gives you some useful way of looking at the, like when you study algebraic curves and you want to understand this moduli space of all algebraic curves. Like knowing behavior of Weierstrass points can help you understand the structure of this moduli. Like one motivation.
Okay. So when we compare graphs and manifolds, it seems that the number of vertices should correspond to the dimension of the manifold. Is that correct? Or
I think that's true for some ways of looking at this analog.
So what is the correct?
I think for me, I think the perspective I have is that for me a network, like a graph or network, is always a one-dimensional object. And to have an analog of a, say, an n-dimensional manifold, the analog would be an n-dimensional CW complex. So you not only have edges between vertices, but you have like triangles and higher dimensional simplices.
So that interpretation works for periodic curves.
In some, for some generalization. So it's true that if you have an n-dimensional algebraic variety and you look at it over a non-Archimedean field, like the CI numbers, it's true that you can get, like when you reduce mod p, you get some singularities, and there's a dual complex. The dual complex will be an n-dimensional simplicial complex, and I think there's certain results about, do the homotopy type of this simplicial complex tells you something about the structure of the variety. I think like the things I described today though, one big reason this doesn't extend naturally is that the notion of effective resistance is something unique to one-dimensional, like these one-dimensional cases, although that there has been some recent work about generalizing the definition of effective resistance to an n-dimensional simplicial complex as well, but that's not something I don't understand very well.
Yeah, regarding this effective resistance, the most natural interpretation is by electric circuit theory, right?
Right.
But is there a more mathematical kind of an aspect without using electric circuits?
Right. Well, I think if you want to explain it just within mathematics, one perspective is like the combinatorial perspective is you think about it as a ratio of spanning trees. Like
but
spanning
that
tree
formula
yeah.
is not so natural. I mean, unless it is the resistance of using electric circuits. Otherwise, it's not natural.
I agree.
It has length.
Sorry?
Can consider that thing as length of the page.
The
buffer. Your weight, your LE.
Yes. The LE. I said it describes the resistance on that individual edge, but you can think of it as length. Or I would. Yeah, I tend to think about it as length or resistance interchangeably.
I was trying to mention that the numerator in that formula of your resistance is the volume of the tropical Jacobian. And it seems the denominator should correspond to some codimension 1 for the integral.
Oh, right. Well, I think it's actually the denominator that's the volume of the Jacobian. But right. So in this formula, there are ways of justifying or motivating what these expressions come from in terms of tropical geometry, like they're connected to the tropical Jacobian.
So then you take a periodic curve, you have to have a special graph. Right? So you take a periodic curve and you can Jacobian. And what is, so is it, what is the shape of polytope?
Right. So, in the classical case for an algebraic curve, the Jacobian will be a complex torus.
Yeah.
And then for the tropical analog, the tropical Jacobian will be a real torus. So it is like you have this same property. It'll be the dimension of the torus will be the genus of the curve, and and you can decompose it into pieces where each piece is indexed by a spanning tree in the tropical case. Yeah, but I mean, I think here the denominator gives you the volumes of Jacobians where you forget what I and J are, and like the top part of the numerator, it does depend on the choice of I and J. But yeah, I mean, I guess this will be the volume of the Jacobian of this quotient graph. Yes, I think this also provides
The thing that Matt Baker observed is that the chance measure on the graph is actually some like random break devices, like the distributions of some sort of random break devices on the metric graph. So
right.
And then you can use the tropical Jacobians to look into how you talk about random break devices. So I don't know if there is some connection there.
Okay, right, yeah. Yeah, I think that also gives a useful perspective. Yeah, I think mathematically too, like thinking about if for effective resistances, you can instead think about random walks or random spanning trees, and that produces the same structures without needing to add some physics.